Alright, so now let's talk about the most basic technique for modulation, which is fundamental modulation, right? As we saw in single phase voltage source converters, fundamental modulation essentially implies that there's only going to be one switch switching only once on each power cycle. And by switching, I mean on to off and then off to on, right? So both transitions happening. So in three-phase voltage source converter, we saw that there are three legs. So there are essentially six switches. So that means each of these six switches would be switching once a power cycle. So let us go ahead and see how does it look like. So we have three-phase voltage source converter. Let me start with a three-wire system. So I have A phase. Sorry, let me bring A phase from. Okay, anything is fine. Let's say this is A phase. This is B phase. And this is C phase. And if you see on the DC link, although if it's a three-wire system, you don't necessarily need this middle point. Let me call it as O. So this could not necessarily be an actual middle point because nothing is connected here. It could be a fictitious point also, which we are just imagining, right? So it could be just something which we are doing it for the derivation. But if it's a four-wire system, then you physically need the point O so that you can generate the fourth wire, which is going to be the neutral wire. So let's start with analyzing this circuit. So we would use certain terminology. So voltage V AO, VBO and VCO. These voltages we will call it as pole voltages. Right? Voltage with respect to this point O, we would call it as pole voltage. Obviously VAB, VBC and VCA, these are line voltages. And now if this system is also connected to a load, let's say an RLE kind of load, it could be a machine, for example, right, where you represented it by the back EMF and a series resistance and inductance. And this is again a three-wire load where the neutral is tied up. If this is how the load is connected, in that case voltage VAN, VBN, VCN across the load are the phase voltages. So one thing you should note is the pole voltage and phase voltages are different. Pole voltage is defined with respect to the inverter. Phase voltage is defined with respect to the load. Although if you connect point O to point N and make it a four-wire inverter, in that case both phase voltages and pole voltage will become equal. So let us start by drawing these different voltages. So let's say VAO. Now what if you see VAO, if you only see leg A, that essentially means it's a half bridge single phase inverter, right? So how can you do a fundamental modulation? You can keep the voltage plus VDC by 2 for some time. Then you can keep the voltage minus VDC2 for some time. Right? So this is full period 2 pi. And this is pi. This is VAO. Now VBO, as we understand, BO voltage is going to be 120 degree lagging from VAO. So therefore VBO will be 120 degree lagging. So therefore it will start from here, go till here, become negative, continue. So I'm only drawing this till point and it will come from here. This is VBO, and similarly you can draw VCO, which is going to be further 120 degree lagging VBO. Let me extend these points. All right, so now these are a VAO, VBO. VCO is further 120 degree lagging, so VCO will start from here, go like this, and come back, right? So this is how the pole voltages VAO, VBO, VCO would look like, wherein the magnitude is VDC by 2 and minus VDC by 2, the values at the top and the bottom. Let us now draw the line voltage. Let's say VAB. How would VAB look like? VAB is going to be VAO minus VBO. So you can just do the subtraction and you can draw VAB. VAO minus VBO, it will be minus minus plus, so it will be VDC. VAO minus VBO, again minus minus plus, okay. VAO minus VBO to be 0. VAO minus 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 minus, another minus, and then another 0. This is how your line voltage VAB is going to look like. Similarly, you can draw VBC and VCA also. Now the next interesting thing is, how would the phase voltage look like? How would the phase voltage VAN look like? If it's a 4-wire system, which essentially means that potential between N and O, they are shorted, so potential between N and O is 0, and therefore VAN is nothing but VAO. We have already drawn VAN, so the same waveform is applicable for, we have already drawn VAO, same waveform is applicable for VAN. So in 4-wire system, it's straightforward. Let us see what happens in a 3-wire system. So in 3-wire system, what we need to find is essentially the relationship. If you want to find VAN, you need to find the relationship between VON. So if you can somehow find the relationship between VON, then we can write VN in terms of VON and VAO. So how do we find relationship between VON? Let us write the Kirchhoff's voltage law for corresponding to each phase for the load. So for the load, so writing Kirchhoff's voltage law for load, use other color pen. I can say that VO starting from point O plus VAO, so I have reached now this point A, these are shorted obviously, A to A, B to B and C to C, minus L dia by dt minus Ia into R, this is R, this is L, and let me call this one as V small a minus V small a is equal to V at N. I've reached this point N. So this is Kirchhoff's voltage law starting from point O going till point N. So we started with potential of O, gone till potential of N. Now similarly we can write it, start from potential O, go through phase B and again reach N, start from O, go through phase C and again reach N. So there will be two more equations. So let me write those two equations, VO plus VBO minus LdIB by dt minus IB into R minus VB is equal to Vn, and similarly VO plus VCO minus LdIC by dt minus IC into R minus VC is equal to Vn. Let me add these three equations now. So if I add these three equations, I get 3 times VO plus VAO plus VBO plus VCO minus L times D of IA plus IB plus IC by dt minus R times IA plus IB plus IC minus VA plus VB plus VC is equal to 3 times Vn. So I've just added the three equations. If you see the circuit, currents IA plus IB plus IC has to be 0, Kirchhoff's current law, right? Because neutral is open. It's a 3-wire system, so therefore all the 3 current sum must be equal to 0. And that is the reason, so IA plus IB plus IC must be equal to 0 because of Kirchhoff's current law in a 3-wire system, right? Also, you can say that VA plus VB plus VC is going to be 0 if it's a balanced source. If it's a balanced source, then this is also going to be equal to 0. So with this assumption, we can rewrite the top equation and we can say that 3 times VO plus VAO plus VBO plus VCO. This third term will be 0, fourth term would be 0, fifth term would be 0 is equal to 3 times Vn. In rearrange, you can write VNO, which is nothing but Vn minus VO, which is equal to VAO plus VBO plus VCO upon 3. This is the equation for VNO, which is the sum of the pole voltages divided by 3. Alright, now let us try to draw this waveform in the same graph. So let me use the same axis here. Let me also draw VNO. So VAO in the first period, if you see, VAO is plus VDC by 2, VBO is minus VDC by 2, VCO is plus VDC by 2. So if you add, you get VDC by 2 divided by 3. So you get VDC by 6. So you get a positive VDC by 6. Then in the second, if you add, you will get minus VDC by 6, then again plus VDC by 6, then again minus, then again plus, then again minus, then again so on. So this level is nothing but VDC by 6. This is minus VDC by 6. This is how your VNO, which is neutral to pole voltage, would look like. Okay. Now, if you want to draw the phase voltage was VAN. We can say VN is equal to VAO minus VNO, right? We can write it as VAO minus VNO. So if we do that, then if I substitute VNO from this expression, I can write it as VAO minus VAO plus VBO plus VCO upon 3, which I can rewrite as 2 times VAO minus VBO minus VCO upon 3. This is going to be expression for VAN. You can similarly derive expression for VBN as well as for VCN. Let us try to draw this waveform now. Let's try to draw VAN here. Extend the points. Okay, so VAN is VAO 2 times VAO minus VBO minus VCO upon 3. So in the first period, if I see, it is 2 times VO means VDC. So it's going to be 2 times VDC, sorry, 2 times VDC by 2, 2 into 2 VDC, 2 into VDC by 2 minus VBO, which is itself minus VDC by 2, and VCO, which is plus VDC by 2. So they would just cancel out, divided by 3. So it will be VDC by 3. Let me just mark it here. Let's say this is VDC by 3. In the second period, if you see, in the second period, VAO is same. VBO is minus VDC by 2, and VCO is also minus VDC by 2, whole divided by 3. So this is approximately VDC 2 VDC by 3. So the first one was this, let's say this is 2 VDC by 3. First one was VDC by 3. And then you have third also, you can check it yourself. Then you'll have fourth minus VDC by 3, minus 2 VDC by 3, again minus VDC by 3, and again 0. This is how your phase voltage is going to look like in this scenario, VAN. In case of a 3-wire system. So now if you see these waveforms, right, you can say they have some number of levels. Now what is levels? Levels means essentially steps. So for example, if you observe VAO, then it looks like it has 2 levels. That means plus VDC by 2 and minus VDC by 2. Similarly, if you observe VAB has 1, another is 0 level, and the negative level. So it has 3 levels. And if you see VN, you have VDC by 3, 2 VDC by 3, minus VDC by 3, minus 2 VDC by 3. So it has actually, as visible, it has 4 levels. In general, the number of levels in pole voltage, if they are equal to P, which in our case is equal to 2, then number of levels in line voltage is going to be L, which is going to be 2P minus 1, which is 3 in our case. And number of levels in phase voltage, we call it as M, which is 2L minus 1, which is 5. Now you might say that there is something wrong with this formula, because we just saw that the number of levels we have in the phase voltage is 4, but here you are saying it's 5. So these 3 things are generic. They are not for the fundamental modulation only. They are applicable for all kinds of modulation, sine, triangle. So these are like the basic principles of the circuit. It has nothing to do with modulation scheme. So they are like, and these are the maximum number of levels. So in sine, triangle, space vector, and so on. In our fundamental modulation, what happens is there is never a scenario when the top switches, let me call it as SC1, SB1, and SA1. There's never a scenario when all the top 3 switches are on. You can see the waveforms. But then in other modulation scheme that happens. And when that happens, when all the top 3 switches turn on, then you can see this basic formula, which is VAN. If all the top 3 switches are on, then VAN will actually be 0, right? So you will have another 0 level, which is not visible in this VAN waveform at this stage. So therefore these are 4 level plus a 0 level gives you total 5 level, right? So this thing is applicable, and rather than saying it's number of level, these are actually the maximum number of level. You can still do a modulation. For example, let's say you never turn on any switches, so you always get 0. So you get 0, 0, 0. So you get 0 level, you get 1 level in all the 3 of them, right? So it's better to say that these are the maximum number of levels in the circuit, and these are applicable for any modulation scheme. So far so good. So in general we would call this circuit as a P level converter or inverter. For example, the one which we discussed above is actually a circuit which is a 2-level converter or inverter. We are not going into multi-level converters, but essentially what is a multi-level converter? Wherein you have more P, so you can have P equal to 3, 5, and then anything, whatever you want, depending on how your circuit behaves, right? So you may have to have a more complex circuit, you may need more number of active devices, but you can generate a higher number of levels more than 2, and those circuits we typically call it as multi-level converter. So the one circuit which we are seeing now is a 2-level voltage source converter. So we can always also, this is a 3-phase voltage source converter. The one which we are seeing is specifically called as a 2-level 3-phase voltage source converter. You can have 3-level 3-phase voltage source converter. You can have higher level 3-phase voltage source converters, right? Okay, so this is so far so good. I would like to point out one more advantage of having this 3-wire configuration versus a 4-wire configuration. Let me try to draw a figure and then explain that. Okay, now let's say a 3-wire versus a 4-wire. Now you have a load here. Let me now represent load only as a black box. So this is A, this is B, this is C, and this is your N. We have seen that the voltage, for example, VAN, if you observe voltage VAN, let me just go above a little bit for you. If you see VAN is based on fundamental modulation, so it can have lower order harmonics also, it can have third harmonic also, right? So if VN has third harmonic, let's say it would be something like magnitude V and sine of 3 omega t, right? It will be something of that sort. Similarly, VBN could also have third harmonic voltage, right? Which could be, let's say, V sine of 3 times omega t minus 120, which is nothing but equal to V times sine of 3 omega t. And similarly, VCN can also have third harmonic, which will also come out to be V sine 3 omega t. Let's say these corresponding 3 voltage third harmonic tries to force a current corresponding to the each branch, and the current in A phase, third harmonic current in A phase is A sine 3 omega t, current harmonic in B phase is A sine 3 omega t, so equal current, where A represents the ampere here, A sine 3 omega t. So these are the 3 currents flowing in the 3 phases of the load. Now if it's a 3-wire system, that means your neutral is not connected anywhere, neutral is floating. In that case, because of KCL, third harmonic current of A phase plus third harmonic current of B phase plus third harmonic current of C phase must come equal to 0. And if you substitute these three currents here, you would get the only solution possible is A equal to 0. That means you will not have third harmonic current in any of the phases. No third harmonic current in any phase. So you see, this is a significant advantage, because although your voltages had third harmonic, now you have actually removed third harmonic in the current. So effectively you can use it, and you can imagine there is no third harmonic current flowing in the motor. For example, if it's a motor, if load is a motor, so that means there's going to be no torque oscillation because of that third harmonic. Not just third, all triple N harmonics, all triple N harmonic current is 0. So third harmonic, ninth harmonic, 12th and so on. Sorry, all sixth is anyway 0, 12th is anyway 0 because of the symmetry. They are anyways even harmonics. So these are anyway 0, right? Because our waveforms, if you see again here also, if you see VAN waveform, it's a quarter wave symmetric waveform. So these are all the even triple N harmonics are anyway 0. So these are, now we can say further we are able to make the odd triple N harmonics 0. That means 3 into 1 3, 3 3s are 9, 5 3s are 15, and so on. So this is an advantage. If you had a 4-wire system, that means if neutral is connected to the pole voltage, in that case the third harmonic will have a path for the current to flow, and you will not have this advantage. This is whatever we just discussed forms the basic principle of space vector modulation. Right? Space vector modulation, if you see that the basic space vector modulation would have third harmonic voltage, but it does not have any third harmonic current. So that is maybe once we discuss about space vector modulation, I would bring your attention back to this point. Okay, let us stop our discussion on fundamental modulation here. We have actually gone a little bit extent after fundamental modulation. So whatever we have discussed here in terms of the number of level and in terms of the 3-wire versus 4-wire, that goes beyond fundamental modulation. Now let us try to talk about some of the other modulation schemes.